Why do some reactions happen in femtoseconds when others don't happen at all? We know that, almost without exception, reactions need to go uphill in energy before they can go downhill to products. The height of that energy barrier is a key piece of information. It determines whether a reaction occurs instantaneously or whether you'll be waiting until the heat death of the universe for it to finish. But can we actually find that barrier computationally? Can we predict the reaction rate? First, we need to find the geometry at the top of that energy hill. This is called the transition state structure, and today I'm going to show you how to find them. In a past video, we talked about geometry optimization, finding the lowest energy structure of a molecule, an energy minimum at the bottom of a valley. But transition states are fundamentally different, and this is where we hit an impasse with molecular mechanics. Remember, molecular mechanics treats bonds like springs. You define which atoms are bonded, and the force field calculates energies based on how stretched or compressed those springs are. But what happens when a bond is breaking or forming? Molecular mechanics has no concept of this. To either a bond exists or it doesn't. There is no in-between state where electrons are redistributing. Quantum mechanics, on the other hand, actually calculates the electronic structure. It can describe that fleeting moment when electrons are shared between the developing product and that which used to be the reactant. So if you're trying to locate a TS structure, a structure that exists only because of how electrons are rearranging, you need a method that knows about electrons. That means QM, period. Alright, let's talk about what we're actually looking for. In geometry optimization, we found minima, the bottom of energy valleys. Every direction you move, the energy goes up. A transition state can be described using mathematical formalism that is just a bit more sophisticated. It's called a first-order saddle point. Picture a mountain pass between two valleys. If you're standing at the pass and you look toward either valley, you're at a maximum. You could roll downhill in either direction. But if you look along the ridge, perpendicular to your path, you're at a minimum. Moving sideways would take you uphill. That's a saddle point. It's a maximum in one direction, but a minimum in all other directions. Now translate this to molecules with a lot of degrees of freedom. That one special direction in which your system is at an energy maximum is called the reaction coordinate. It's the path that connects reactants to products through the transition state structure. But in all other directions, all other ways the molecule could wiggle or distort, it's actually a minimum. It's stable in every other sense except for that reaction coordinate. For all but the simplest of molecules, we're not talking about 2 or 3 dimensions here. A molecule with n atoms has 3n-6 vibrational degrees of freedom. So a transition state is a minimum in 3n-7 of these degrees of freedom, and a maximum in exactly 1. That's what makes them so tricky to find. You're searching for a very specific point in a high-dimensional space. So how do we use computational chemistry to find these saddle points? One of the most intuitive methods is the bond scan. The idea is beautifully simple. You pick a coordinate that you think represents your reaction, usually the length of a breaking or forming bond, but it sometimes will be an angle or a dihedral bend. At each step, you freeze your chosen coordinate at a specific value, let all other coordinates relax to minimize the energy, and then record that energy. Then you plot your energy at each step versus the reaction coordinate. What you get is a slice through your potential energy surface, and somewhere along that slice, you should see a maximum. That's your approximate transition state geometry. This gives you a great starting guess for your TS optimization, which we'll talk about shortly. Let me show you an example where this works beautifully. A carbene cycloaddition is a reaction in which a carbene, a neutral carbon atom with 6 valence electrons instead of 8, reacts with an alkene, resulting in substituted cyclopropanes. Carbenes can react as electrophiles or nucleophiles depending on their substituents, each having unique characteristics in their TS structures. The 2 new bonds form almost at the same time, within 100 femtoseconds of each other, making the reaction technically concerted. Even so, one bond forms before the other as the carbene approaches at an angle, and we can leverage this information for our TS search. The trick here is to perform a bond scan from your substituted cyclopropane product. Take one CC bond and stretch it from its equilibrium length to about 2.5 or 3 angstroms in small steps. At each step, you let everything else optimize. This is essentially reversing the reaction, and it's much easier to locate the transition state structure this way than starting from separate reactants. The energy climbs as you stretch the bond until you eventually hit a maximum. That's your transition state guess. Then you take that geometry and run it through a true TS optimization calculation. Okay, so let's say that you've run a successful TS optimization and your calculation has converged. Are you done? Nope. You need to verify that the TS structure that you found is in fact the one that you were looking for. This is where vibrational frequency analysis comes in. And I apologize, but the terminology will get technical for a minute. When we calculate vibrational frequencies, we're analyzing the Hessian matrix, the matrix of second derivatives of energy with respect to all nuclear coordinates. The eigenvalues of this matrix tell us about the curvature of the potential energy surface at that point. You can look up these concepts in linear algebra texts if you're curious. For a minimum, the curvature is positive. Every direction curves upward like at the bottom of a bowl. Mathematically, this means all your vibrational frequencies are positive real numbers. But for a transition state, the curvature in one of your dimensions is negative. It curves downward like the top of a hill. So when you see your frequency output, you're looking for exactly one negative or imaginary frequency. If you have 0 imaginary frequencies, you found a minimum, not a transition state. If you have 2 or more imaginary frequencies, you found a higher order saddle point, which is not a transition state either. One more caveat, even when you only find one imaginary frequency, that still doesn't mean that your answer is correct. Typically, for bond breaking or forming, you're looking for imaginary frequencies within around -200 to -400 wave numbers, or inverse centimeters. If you see an imaginary frequency that's smaller than around -100 wave numbers, that's usually an artifact or a methyl rotation or some other dimension that's not associated with your desired reaction coordinate. If possible, you should try to animate this mode, this vibrational mode, to make sure that it corresponds to the bond breaking or bond forming that you expect. I do this in Gauss view because it's easy, but there are probably other ways to do this as well. To summarize, the workflow is bond scanned to find approximate transition state structure locations, perform a constrained minimization to pre-optimize your transition state, run a full TS optimization with a proper algorithm like Bernie algorithm for transition state structures, perform a frequency calculation to verify that there's only one imaginary frequency, and then animate the mode to confirm it's the right reaction. You can also run something called an IRC, intrinsic reaction coordinate, to see if your reactants and products are formed from your desired transition state. That's also another way of validating, but we're not going to discuss that technique specifically in this video. But what about more complex reactions where the reaction coordinate is multidimensional or maybe not so obvious? What if your reaction involves the formation or breaking of multiple bonds simultaneously? For example, take a Diels-Alder cycloaddition. This is where a diene reacts with a dienophile to form a 6-membered ring. 2 carbon-carbon bonds form at the same time. There's no reaction coordinate in the sense of one bond breaking or one bond forming. The transition state involves complex coordinated motion of multiple atoms. I'm not going to sit here and tell you that these transition state structures are trivial to find. You can try multi-dimensional scans, but they can get expensive and time-consuming, if they even work at all. You can try interpolation methods like nudged elastic band or growing string methods, but we won't discuss those here either. You can and should rely on chemical intuition and maybe a little bit of hope, but honestly, for complex reactions like these, especially if you're newer to computational chemistry methods, I'd recommend using an automated tool. Now, I haven't been paid to say this, but if you would like to try some of these reactions yourself, one service I'll point you to is called Rowan. It has an intuitive GUI in which you can draw your own reactants and products and easily predict transition state structures for all sorts of reactions. This makes the entire process really a lot more accessible. The analysis is pretty easy. All structures and data can be exported with a click, and there's a free tier that allows you a certain number of calculations that replenishes each month. Now, I'm not saying you should always use or rely on automated tools. The manual approach teaches you so much about underlying chemistry and physics. You develop a kind of chemical intuition about what transition states should look like and why. In fact, I would recommend that the aspiring computational chemist avoid these tools altogether, at least in the beginning of their education. But for casuals, there's really no shame in taking advantage of these tools. They were engineered specifically for that purpose. Science can move forward when we build on reliable tools rather than reinventing everything from scratch every single time. Let's come back to where we started. Can we predict the rate of a chemical reaction? And the answer is yes. That's exactly what transition state theory allows us to do. This is the Eyring equation. The rate constant depends exponentially on the free energy of activation. this delta G with a double dagger, which is the free energy difference between your reactants and your transition state structure. Kb is the Boltzmann constant, T is temperature, H is Planck's constant, and R is the gas constant. This prefactor before the exponential works out to be around 6 times 10 to the 12 per second at room temperature. We've considered how to determine transition state structures. By comparing with the computed energies of your reactants, we can calculate the free energy of activation that's needed to determine the reaction rate. With this, you're free to predict reaction rate constants. You will be able to understand and describe why one reaction is 1,000,000 times faster than the other reaction. For diastereomeric ratios and antioselective reactions, you'll be able to describe why one forms rather than the other one. So let's recap what we learned. Transition state structure determination requires QM if bond breaking or forming is involved. Molecular mechanics can describe rotational barriers, but only partially. A transition state is a first-order saddle point, a maximum along the reaction coordinate, and a minimum in all other dimensions. We verify transition states by finding exactly one imaginary frequency. Bond scans are your friend for locating approximate TS geometries. Constrained minimization plus TS optimization is a very powerful workflow. For more complex reactions, automated tools like Rowan can save you a lot of headache. Finding transition state structures is both an art and a science, one that I've honed during a lot of graduate work, and one that still causes me to scratch my head sometimes. Algorithms and special tools can help, but chemical intuition and experience are what really make you successful, so don't give up. And once you can reliably find transition states, you've unlocked one of the most powerful capabilities in computational chemistry. You can predict which reactions are possible and how fast they happen. If you found this helpful, check out my previous video on geometry optimization. Please like, comment, and subscribe down below. It really helps small channels like this one. Stay tuned for more comp chem and scientific content. Thanks for watching.